All right, now that we know what a sequence is, let's talk about convergence of a sequence. So we say that a sequence converges to a value L if the limit as n goes to infinity of the terms of the sequence is equal to L. So convergence is just a fancy way of saying that the sequence goes to something. If this limit does not exist, then we say that the sequence diverges. And if the limit goes to if the limit is plus or minus infinity, we still say it diverges, but we say, to be more specific, we say that it diverges to infinity, or to minus infinity, I guess, if it's going to minus infinity. The reason that going to infinity counts as diverging is because if you remember back to your limit laws, right, back when you learned about limits, one of our limit laws, just as an example, was the limit as x goes to a of f of x times g of x is equal to the limit as x goes to a of f of x times the limit as x goes to a of g of x. But this is only true if those two limits exist and are finite, right? So infinity doesn't give you the nice behavior that you would like from limits, and that's why we don't want to count the limit being infinity as converging. Okay, so for example, for what a and b does this arithmetic sequence converge, and if it does converge, what does it converge to? All right, well, if you just look at this formula, a n plus b, right? If a is positive, right, we're adding more and more copies of a as n gets bigger and bigger. So the limit as n goes to infinity of a n plus b, well, this part here is going to get bigger and bigger and bigger because a is positive and we're multiplying it by a number that's going to infinity. So this is going to infinity, right? So this diverges to infinity. On the other hand, if a is less than 0, well, now we're asking about the limit of a n plus b, and this n is still going to infinity, but if a is negative, this first term here is going to negative infinity, and so the whole thing is going to go to negative infinity. So this diverges to negative infinity. And then if a is equal to 0, well, now we're taking the limit as n goes to infinity of 0 times n plus b, but that's just b. Of course, this isn't a very interesting sequence because every term in the sequence is b. So this does converge, but not in a very interesting way, right? Everything in this sequence is just b. And b can be anything. Okay, let's look at geometric sequences. So what about the geometric sequence a over r to the n? Why did I put this over r to the n? I don't know. I meant for this to say a times r to the n. Okay. So let's think about this in a similar way. Right, so we're going to be raising r to powers. So you have to break things into interesting cases, you have to think about what happens when you raise things to large powers. Well, if r is big enough, this is just going to blow up to infinity. So one case is going to be when r is bigger than 1. Right? If r is bigger than 1 and you start raising it to powers, then this r to the n part of the formula is going to go to infinity, and so a r to the n is going to go to plus or minus infinity, depending on whether a is positive or negative. And so this is going to diverge to plus or minus infinity. Okay, let's think about when r is equal to 1. Well, if r is equal to 1, r to the n is just always equal to 1. And so our sequence just looks like a. It's always a. And that's going to go to a. So this converges to a for very boring reasons, because every term in the sequence is just a. Okay, now let's look at what happens if r is small. And when we're talking about raising something to larger and larger powers, small means between -1 and 1, because then if we raise r to very large powers, well, as long as r is between -1 and 1, when you raise it to a large power, it's going to go to 0, right? And if r to the n is going to 0, then a times r to the n is going to 0. And so this converges to 0. Notice that this isn't a trivial statement, right? In the previous example, every term in the sequence was a because the ratio r was 1. And so, of course, that goes to a. But in this example, right, our terms are actually different. The terms in the sequence are a, and then a times r, and then r squared times a, and so on. So they're actually all different, but they're actually going to something this time. Okay, and then I guess the final case is when r is less than -1. Okay, if r is less than -1, then, well, let's see. The absolute value of r gets big, right? Because the absolute value of r is a big positive number, a positive number greater than 1. But since r itself is negative, when you raise it to larger and larger powers, its sign keeps flipping back and forth, right? Because even powers of a negative are positive, and odd powers of a negative are negative. So r to the n, right, if we looked at a graph of it at integers, it's going to be jumping up and down and up and down, but because r is less than -1, these jumps are going to be increasing in size. So this limit just doesn't exist. So this time the limit doesn't exist. And so the geometric sequence in this case diverges. Okay. A couple more examples. Let's look at this sequence, the sequence 4n plus 4 over 3n minus 7. Does it converge, and if so, to what? Remember, when we ask about convergence, we're really just calculating a limit, right? And we already have lots of tricks for calculating limits that you might remember from your Calc 1 days. Right? The thing about sequences is if we write a sequence using a formula like this, it looks like it's a real valued function, even though we're only thinking of it for integer values of n. So most of your function tricks for limits will still work. For example, for this kind of limit, a ratio of polynomials, so a rational function, a good trick for this kind of limit at plus or minus infinity was to multiply the numerator and denominator by some well-chosen value, power of n. And in this example, the right power to use is the first power. Okay, so if we distribute this in the numerator, we get 4 plus 4 over n. And in the denominator, we get 3 minus 7 over n. And now when we take the limit as n goes to infinity, this part goes to 0, this part goes to 0, and so we get 4/3. So this sequence converges to 4/3. Maybe you could have said that without doing any calculation. You might, depending on your familiarity with these kinds of limits, you might have just noticed, oh, since these powers of n are the same, it's going to be 4/3. Another trick that works for sequences as well as it works for any other limit is a tricky thing like this. So what about this sequence? Does it converge? And if so, to what? Well, this is actually kind of tricky because, right, the denominator we understand pretty well. It's just n. But the numerator is actually kind of tricky because sine of n jumps around a lot, right? If n ever hit an exact multiple of pi, that term would be 0. But the thing is, pi is irrational, and so n, the integers, are never going to hit an exact multiple of pi. If a multiple of pi was an integer, let me write this out. If you had some multiple of pi that was an integer, let's say an integer q, but then you could divide both sides by whatever the multiple was, and you'd have pi is a rational number, but pi happens to be irrational. In fact, it's transcendental, so this can't happen. So what is happening in the numerator here is very difficult to know much about, right? So hard to say what's going on with these individual terms because the numerator is kind of complicated for integer values of n. But the thing is, so you might remember this trick again from your Calc 1 days, the thing is this numerator, it never gets bigger than 1 because, well, it's the sine function. So one thing we can say about this is that the numerator is never bigger than 1. So less than or equal to 1. All right, so the whole fraction sine n over n is definitely less than or equal to 1 over n. Also, this numerator never gets smaller than minus 1. So on the low side, we can say that sine n over n is never smaller than minus 1 over n. Okay, now you probably by now you know what's coming next. Now we can think about the limit as n goes to infinity because, right, our whole goal to decide on convergence is to right, we're asking about convergence. To decide on convergence, we need to know what happens to the limit of the sequence as n goes to infinity. So on these two sides, if we take the limit as n goes to infinity, well, on the ends, minus 1 over n as n goes to infinity, that's 0. And 1 over n as n goes to infinity, that's also 0. But the sine n over n is trapped in between these two. And so its limit has to be between 0 and 0. That means that it's 0, right? This is our old friend, the squeeze theorem. Right? The squeeze theorem is not just for functions. It's also true for, well, really any limit, right? So you can use all of the limit tricks that you already know for deciding if a sequence converges, except for L'Hopital's rule, because L'Hopital's rule depends on, well, you have to be careful with L'Hopital's rule, because L'Hopital's rule depends on the thing you are taking a limit of being a differentiable function, and our sequences only take discrete values. They aren't continuous. So L'Hopital's rule is dangerous. But all the other tools, like the limit laws and the squeeze theorem and algebra tricks, you can use to evaluate limits of sequences, and so you can use those to decide if a sequence converges or not.